rolling on through. Last talk before lunch. We have Feng Liu from Melbourne. Did his PhD in Sydney, and also has been visiting at Riken in Japan, kind of throughout his whole academic career. I met him when he came to visit the Gatsby unit like a month after I left. And then I heard through the grapevine that he was doing the project that I had basically done 3 years before. And I was kind of annoyed, oh, why didn't you read my paper that did this already? And then I saw what he had done and it was way better than what I had done before. So it was good that he came back and solved the problem better. So he's done a bunch of stuff about like reliability and connecting adversarial examples and statistical testing. But he's not going to talk about statistical testing because a lot of that works with me and that's silly. So instead, he's going to tell us about some kind of model reprogramming crazy stuff.
The interest mainly in statistical testing as with CAIDA, about the independent testing, summer testing. And another stuff is also related to distribution shift, like distribution shift detection or learning on the distribution shift. In my research, I mainly takes care of 3 kinds of shifts. The first one is adversary shift. The second one is output distribution shift. The third one is nature shift. Nature shift means that we might meet something like naturally happening in our life. For example, we have model trained with images taken at daytime. And if we want to transfer this knowledge and use it to the image taken at night, so it's kind of nature shift. And we'll also meet something like weather change and something like sunshine change, and it's called nature shift. In nature shift, we mainly talk about the adaptation, and we want a model more adaptable to this kind of nature shift. And today, I will talk about something regarding nature shift. It's called fine-tuning technology. It's called reprogramming. So in model reprogramming, we may have 2 modules. The first one is input reprogramming. The second one is output back. In this talk, I'm going to talk about 2 of our methods in this year, and one about input reprogramming. The second one is about output back. In the last section, I will show some useful resources for this direction. So, what is input reprogramming? I don't know if how many people know adversarial attack. Yeah, just okay. So in adversarial attack, it's we want to add some small perturbation to the images, and such that the model can be totally full. For example, we got this image, panda image here, and we also have well-trained classifier. And for that classifier, we classify this image as panda with this confidence level. And then we can just design this kind of special noise, and it is noise with panda image. We got another panda image. From our human eyes, we cannot recognize what's the difference between this one and this guy. We didn't see any difference. But for the previous well-trained model, and it will recognize panda as given with very high confidence. It is called adversarial attack. And why adversarial attack can be successful? Because neural network is quite sensitive and overconfident. We just make small change on input space. The output will change a lot. So in the adversarial attack, they use this property try to attack the model to make this model embedded in the development part. Okay, that's called adversarial attack. Now let's think about this. What's the reason behind the success of adversarial attack? The reason is that the neural network is very sensitive to input. So it is small noise to the neural network. Neural networks will change a lot. So we can use it to do the bad thing. Of course, we can use it to do the good thing. What's good thing here is adaptation. This idea is proposed in IPR 2019 by English fellows. And in their task, they just consider a preacher model. The preacher model is ImageNet classifier. And what is their task? Their task is to count how many like the white squares inside this image. Okay, inside this image. You can say recognizing image side is totally different with this task. Okay, it's totally different with this task. But in their paper, they just reprogram this guy and to count numbers, how many white boxes within that image. Okay. And how they do that? The first part is input programming. You can say this image, our new task, this image, it's actually quite smaller than ImageNet input, okay, than the ImageNet size. And they will just padding this small image with some noise, And then what is the learnable? The learnable one is the noise, with noise around the small image inside, in the middle. And after we got this one, we can consider it is a tiny noise to this small image, and we feed this noise image to the ImageNet classifier. The classifier will still give us output is about 1,000 classes in the ImageNet data set. So we cannot count numbers either. How to do that? We need another technique called output mapping. Okay, another module. In this paper, original paper, it just got this very hard coding. It just said, okay, so if the y is 10, I will say it will map to one square is inside the image. If there's a goldfish, it will be mapped to the 2 squares in this small image. So for the input mapping, for the input programming, we will add a learnable noise to the image. And for the output mapping, we will just get the map from the original classes. For example, 1,000 ImageNet classes to our target classes. Here, target classes, we just have 10 classes, just like 10 squares. So that is a model reprogramming. And yeah, if we compare adversarial tag and model reprogramming, we will find that in adversarial tag we will add this small noise such that the model just invalid. But in the reprogramming, we will add this small noise image to the maybe it's not small anymore, but we will add this image to this to original to the image in our target site, and to reprogram the model to complete the task on our target model. There are 2 kinds of pipeline for input reprogramming. The first one is padding. So like I said, we will not change the size of our target image, and we will just add padding outside the image, such that the padded image will fit the pre-trained model's input size. Okay, that's padding. Another is the watermarking. Watermarking means that we just resize our target image to fit the model's inputs, In both cases, we will finally learn the pattern, noise pattern, and we will have the mask. And after we turn pattern with mask, and we will add this one together to the padded image or to the resized image. So that's a difference between adversarial tag and reprogramming. And in the model reprogramming, like I said, now we can say the more general framework here. We will often have a source domain, and we use that source domain to get a pre-trained model. Okay, but we do not have any data from the source domain. We only have the pre-trained model here. And we want to reprogram or reuse this model. To complete our task in target domain. So that's model reprogramming. We have 2 models. First one, input visual reprogramming. The second part is output mapping. And for the output mapping, we often want this map can be defined. Okay, not learn this one. And if we look at from from this mapping system, we can say we will have the frozen pre-trained classifier. And for this pre-trained classifier, takes the pre-trained images in pre-trained for training pre-trained model, access, and to get this source table YS. And for the input reprogramming, we'll just map xt to xx. Okay. And for output mapping, we will map the ys to yt. Okay. Ys is a pre-trained labels in the pre-trained model, and yt is labels in our target model. Yeah. So if we just write in what is the final formula will like this. First, we will map xt, our target image, to fit the pre-trained model's input, and then we will use the pre-trained model and get the pre-trained labels. After that, we will just map pre-trained labels to our target label. Okay. And for the outer precise layer, we only have parameters for fin, for input reprogramming, and there is no parameter, learnable parameter in the fout, output mapping. Okay, so that's model reprogramming. Yeah, and the supervised training loss is a pair we just consider supervised learning. We will have a fully labeled data set in the backend in target domain. And we just try to minimize the learnable noise, and to make this loss function minimized. As it's loss function. And why we consider model reprogramming? And because we have a lot of fine-tuning methods. For example, we can find all the model parameters. Or we can just fine-tune the last layer, or we can fine-tune some layers. Okay. Why should we consider model reprogramming? Because model reprogramming is kind of a very efficient fine-tuning way. We only consider the parameters in the input space. Okay. And the input space is much smaller than the parameter space. Yeah, we can look at this. Figure. So when we consider foundation model, of course, we got a very large number of trainable parameters. And when we just train some specific tasks, we train neural network for specific tasks, the required trainable parameters is less than foundation model, of course. And when we consider transfer learning, it's kind of more flexible. For example, we can just turn the last layer, or we can turn maybe 10 to the last layer. Okay. It's based on how many parameters we want to turn, and what's the difference between the downstream task and our pre-trained model data set. Okay. But in model reprogramming, we only consider train input noise. Okay. Our trainable parameter is equal to our input size, and it's much smaller than the previous tasks. And why it can work? Because of the property like neural network is sensitive. If we change input slightly, the whole model's output of each layer will change a lot. So we can use this property, try to reprogram the model to fit downstream tasks. And if we compare the number of parameters, we know if for fully fine-tuning, we might need to train this kind of number of parameters. For linear prompt, we need to train the model's output plus our target, how many classes we have in target domain. And for model reprogramming, it's just input size. Okay, just input size. If we got a lot of classes, for the pre-trained model, and a lot of classes on the target domain, and the linear prompt will also have a much larger number of parameters compared to model reprogramming. So here is our interest. Can we just change the input and try to reprogram model, fine-tune the model? Okay. And if you heard about, the reprogramming might be not that popular term, but if you heard about prompting, actually the same thing. Okay. If you heard about prompting, now you can think about prompting. What is prompting? It's something in the input and model changes, and model output changes. Why does prompting can work? Actually, it shares the same philosophy. Because if we change input slightly, somehow the model output will change a lot. So the prompting, although this term appears after reprogramming, but it's very more popular in our field. So while considering using prompting, it's a model reprogramming. But it's actually on high level they share the same things. Okay, now let's go to some milestone and representative. The first one, I think it's a very easy, just go through it. The first one is watermarking. The watermarking, we will resize xt, just resize xt to access size, so size of input of pre-trained model. And then we add the input, we add the trainable noise, signal. And then for the pre-trained model, it's just fixed. And for output mapping, we can use some existing method to predefine what's the relationship between the labels for the pre-trained model and labels in target domain. Okay, it's predefined. And after that, we just training this data, try to minimize the supervised loss. For example, cross-section loss. Yeah, and here is maybe more familiar for if you read the visual prompt paper. In visual prompt paper, it's just the padding. Okay, we use padding strategy. It considers the original image here, and maybe not that padding, but it's still similar to padding. So we consider the image the side. The side is unchanged, but we will add this and it's free. It's free. Okay, around the image, and this frame is trainable. This frame is trainable. Okay, this frame is trainable, and they can train this visual prompt. Okay, even text prompt. Text prompt is we just need an invisible token, and for our input, and we can train with visual prompt or text prompt. And here, if we want to train with phantom clip, we only need to train visual prompt and text prompt, and keep the clip encoder, image encoder, clip, text encoder fixed. So we can phantom clip. Okay, we can. And if we consider vision model, it's more straightforward. We just add this frame on the original image, and we train this frame. And we also need the hard code mapping to map the pre-trained model's output to the tag domain. And we just optimize this frame, okay, noise frame, and try to reuse or reprogram all. Yeah, and so the padding is more strict compared to watermarking and visual prompting. Padding we will directly use the original size, but add this padding outside of this image, and then also train this frame. We will not train all the trainable parameters. We will train this noisy pattern and outside the image, okay? And follow same procedures to just optimize the parameters. So it is just how we do input reprogramming, And in the literature, we may consider many things to improve that or to make it broader. First one, we can consider more effective prompting basement. Okay. And in the previous slides, we can say if we have the whole data set, target data set, we just learn one prompt. Okay, just learn one reprogram noise for the whole data set. And in the next work, we find that this is quite strict and cannot provide enough flexibility or complexity to fit our downstream tasks. Or we can consider more automated prompt selection or in the more challenging scenarios. And in this talk, we mainly talk about the first part. Okay. It's our work in SML 4. Like I said, a pre-trained determined mask is shared across all images. Considering now we have a data set and we want to reprogram a pre-trained model on our data set. Okay, but we just learn one pattern. To all the images within the data set. So what is the problem here? The problem is that it cannot make the training loss minimize sometimes. It will minimize, but it's not ideal. It cannot reach like a very small training. So that's not good. If we consider this from sample level, we can find that even for this one, so full reprogramming, forward marking, we can say the trainable parameter, number of trainable parameters is larger than the other two cases, but its performance is not consistent. We can say it's just it's for this case, it's just make the wrong prediction, and for the case we have the list number of parameters, it's just make a good prediction here. And if we consider from the training perspective, and we do the statistics to show what's the training loss change, we find that after the training, after the training, some samples, the loss value of some samples are actually increased. It means that if we just consider one shared pattern with all images, it cannot provide enough complexity to cover the complex training set, complex target domain set. So that's the issue. How to address this issue? And in this work, we consider just each sample can use different masks. and use different patterns. In the first work, all the samples share the same pattern. All the samples share the same pattern. And we find that if we just learn this kind of one pattern for all data sets, or for all images in this data set, and we can not obtain a good, maybe we cannot obtain good training loss. That's bad. That's bad. So how can we do that? The first idea is that we can just consider train another neural network to generate the noise or generate noise pattern from each image. But we find that if we consider that way, the generator will need a lot of parameters as well. It's like we want to use one image to generate another image. Okay. Although this image is noise, but we want this image to minimize our training loss. But we find that if we train this kind of generator, the number of parameters required are still large. Still large. So how can we do that? In this paper, consider just using the mask. Okay. We still learn the same pattern, the learnable noise for each resized or padded image. But we will for each image, we'll train this lightweight mask generator. We will generate a mask for each image, and then we just after we got this mask, and then we just turn this pattern into mask. Okay. Because this mask is different for different images. So in the end, the reprogrammed noise is different. Reprogrammed is different for different images in your training site. Okay, so this is our idea. And in this paper, we also did the basic analysis for this model programming. And of course, here, because we provide more flexibility for our function classes, okay, we consider in for the previous studies, if we just consider it one noise, we actually will form the new function classes. Okay, we'll form new function classes. We have pretrain model here, and we change input. And on the input side, we have the learnable noise epsilon. And we actually will have the function classes as well. It's a new function classes. And for this new function classes, only one parameter is epsilon, is trainable noise. And here we introduce another thing to generate this noise. Okay, and we find that from approximation error side, our method will have lower approximation error because we provide more parameters and try to make the pattern is generated by the image, and for each different image, the noise pattern is different. Okay. And for the estimation error, because we only add like for this lightweight mask generator, because we only have the very light parameters. So for the estimation error, it does not increase a lot. I think it's a barely increase. Okay. So from that way, we can know. In this way, sample-specific reprogramming, we can consider, even in theory, we will have the lower approximation error and quite similar estimation error compared to previous methods. And that's why we got good performance on the data side. And here are results. And we compare and we do the pretrain model on ResNet and VIT. It's two free work. And our method is got much improvement compared to previous method by just considering to generate different masks for different images. And it's consistent, and the improvement is consistent. And this is a case is what is learnable, what is learned mask for different images. You can say this mask is actually quite different for different images, and it will cover somehow the previous images, some important part for the previous image. And this noise pattern is shaded, and we got this reprogrammed pattern, and we got a finalized reprogrammed image. And after we feed this reprogrammed image to a pretrain model, this pretrain model might not be, might be different, totally different from our target domain, but we can still get better than good. We also try to combine. We also try to compare this reprogramming with other fine-tuning framework. So it's required by the real space variables. So in reprogramming, we mainly focus on reprogramming model, fine-tuned model from input space, right? It learnable pattern on input space. And another technique called LoRa adaptation, mainly focus on the middle part of the model. And the linear problem or fine-tuning, last layer fine-tuning will focus on the last layer. So it's interesting to compare these three technologies because we actually take care of different parts of the model and try to fine-tune it. And for LoRa, we find that if for fine-tuning LoRa, because LoRa we always need to fine-tune last layer. Okay, always fine-tune last layer. And our some specific mask, we find that our parameter we actually do not have a similar parameter compared to LoRa, but our performance is better. It's better than LoRa plus fine-tuning. Here is also we also conduct SMM plus fine-tuning. Okay. In this table for the mapping part, we didn't consider it's a predefined vacuum. We will still use the fine-tuning to fine-tune that layer, because it's very important for multi-class classification. And so we got this fair comparison with LoRa, and we find that if we consider to turn the last layer, and we actually perform better than LoRa in this case. We also consider compared to fine-tuning. We found that in the multi-class classification, the last layer fine-tuning is very important. If we do not consider the last layer fine-tuning and direct compare our SMM with the fine-tuning, I mean the fine-tuning last layer, SM cannot be fine-tuning in most cases. But we do have advantages for some case, like when the pre-trained model is really far away from our downstream task. In that case, the last layer fine-tuning or linear probe cannot perform well. Because linear probe only change the last layers and they fix how they got the feature. Okay. But if we consider model reprogramming, we change from input layer. When we change input layer, the middle layers output will change a lot. Okay, will change somehow. So that's why when domain is like quite different, the model reprogramming itself can be fine-tuning and have much less parameters than fine-tuning. Fine-tuning often have a much more parameters than the model reprogramming. But in this paper, we consider like more compromised solution. We show fine-tuning and we also show our SM plus fine-tuning. Okay. So in the fine-tuning, we will just last layer fine-tuning. Okay. We will turn the last layer parameters, and in the reprogramming, we turn the input noise. Okay. Of course, we can do it together. And we find that if we do it together, we can get better performance. And we just we didn't introduce much more parameters. I think for model programming, we just if we consider parameters over the pre-trained model parameters, just increase 0.1% parameters. Okay. Even for the fine-tuning, we didn't increase the parameters. Okay, so that's the first part. Is input reprogramming. So for input reprogramming, it takes inspiration from other examples. Actually, in the 2019 paper, the paper title is or the paper motivation is to steal power from pre-trained model. It's still like a attacking scenario, but it's I kind of disagree with that. It's like we actually are using the knowledge within the pre-trained model instead of stealing power from the pre-trained model.
Can I confirm that my understanding is correct? Like this isn't actually different from fine-tuning. It's just instead of fine-tuning the end, you're fine-tuning something at the start.
Yeah, from input space.
Yeah. So like you think of the original model as having an identity layer that doesn't do anything. Like the basic version without SMM would just be like adding biases to that identity layer. And then SMM, you're adding some more complicated structure.
It's like
As
adding more
first.
complicated structure
Yeah.
for the input.
But so like fine tuning both the start and the end, or you can fine tune the start and the end and the middle, like whatever mix of things you want to do, it's all fine tuned, right?
I think here, I think here is I think here maybe we will not consider fine tuning this part. It's just a linear form. Yeah, and I understand.
It's just depends on, like everything is fine tuning, it just depends on what's frozen, right? It's not full model fine tuning, but like linear programming is take the whole network, freeze everything except the last layer, and then restart that.
Yeah, all the network is free. Yeah, all the network is free.
Yeah.
It's not parameters, right? Yeah, not parameters. Yeah.
But it is, it's just a special case of fine tuning. It's not fine tuning the whole network. It's
Yeah.
fine-tuning the part.
Yeah, and it's like we introduce trainable parameters that class specific things. And it's also an alternative to the existing technology to maybe reuse the model. That's maybe a better word. How we reuse the model for our downstream task, or reprogram model to downstream task. Yeah, it's maybe better for that. And we can also combine it with other technologies like lower output. Okay, so for first work for the simpler programming part, it's like maybe we will consider if kind of reprogram patterns can be transformed across different downstream tasks. Here we just train one pattern for one downstream task. We didn't know if this kind of pattern can be transferable. There's one paper published last year to study this. It's interesting direction. Another one is reprogramming use other tasks. As I know, currently it's used for time series and graph neural network already, and it's interesting to explore more scenarios for this technology. Yeah, and last thing is can this pattern can be more interpretable. Someone will just consider. I think in the video from the blinded learn is kind of frame out of the image because it like is kind of interpretable, but it's still I don't think that there's much solid evidence for that. Okay, now let's go to the second part. It's output mapping. So for output mapping, like I said, we want to find the relationship between source label and target label. And this is what we want. And the relationship between source label and target label here. And here in output mapping, we mainly want to ensure all this function f_alt is directly decided, and there is no trainable parameters. Yeah. So if we consider trainable, it will be just become the linear form. And if we consider inference based, it's like we just want to use some way to find the relationship between the label in YT and the label in YX. And there are three works on this. Before our paper, the three representative work is a random, frequent, and iterative label mapping. So random label mapping is like what in did in year 2019. It's just a random assign relationship. Random assign one label to one target label. After that, we can just use this three label only to do the final, the optimization procedure. Okay. That's previous answer is random label. And another work is called frequent label mapping. Why we consider frequent label mapping? Because for different target classes, they might have different relationship between with the source classes. So it might be not reasonable to just random assign their relationship, and we can find what is the most relevant one for each target class. For example, For example, after we somehow reprogram or we resize the image, we can feed the image to picture model, and the picture model will give us this image. I mean, which source class corresponds to your image. Okay. Also, the image, your target image. Okay. So we can find the most frequent one, most frequent YS for this target site, most frequent YS for this target site, and assign the label from most frequent target site, a most frequent source label to one of the target label. Yeah. So that's a frequent label mapping. And in 2023, we found that if we just define or fix the mapping at very beginning, it will not work well. So we consider to iterative label mapping. After each epoch, the mapping, the effort will change. Okay. Although there is no parameters in the effort, here it's just one-to-one label mapping, just a mapping, and there are no any parameters. Okay. But the changes mapping after each epoch will have the better performance. Because at the very beginning the model is here, and maybe they have this kind of statistical relationship, but after a little, maybe one epoch training, and the model actually changes. So we need to decide effort. And if we consider learnable and inference times, we can say the F-in is included programming all the method in this backpropagation to update. And for inference part, for F-out, it's just determined by the forward process. Okay, there is no any trainable parameters within the inference time for this inference-based output instead of linear clock. Yeah, and in this work, I just presented in January 2022, we found that there is a much better way to just confirm many-to-many map between the source labels and target labels, without any trainable parameters. It means that given picture model and a given picture model and a target data site, we can directly decide the relationship between the YS and the YT. There's no action. And first, we can look at what's the drawback for the one-on-one mapping. For one-on-one mapping, for one-to-one mapping, the drawback is clear. For example, we got some image from target site, okay, target domain, and if we fit this image to the after resize, for example, we fit this image to our picture model. Our picture model will give output logics. Okay, maybe this output logics will not be dominated by one class. It might have a relatively higher logics for many classes. In this case, if we just consider one, if we just consider map one source label with target label, it's not lots of information from the picture model, And here is an example for the frequent label mapping method. Yeah. So in this, I think this is picture label, and this is downstream label. Okay. And in the frequent label mapping, we can consider first we got the moving file. Okay. Well, how we match moving one with some classes. And we can say, yeah, because for the moving one, okay, it's already been paired with truck because the truck and the moving one have a much higher match. Okay, after we gave moving one image to after we gave truck image to the picture model, and moving one gets the highest logic for it's 2,000 times. Okay, 2,000 times. Yeah, so it will match. Oh, sorry, it's a 3,000 times. So we will first match truck with moving one. But in the frequent label mapping, after we pair truck with the moving one, moving one will not be feasible or will no longer be paired with other classes. It means that we will never pair the automobile with the moving one. Although they have very high, the high numbers to be paired, to be matched. So that's the issue. And so we want to consider, can we do this from one-to-one matching to many-to-many matching? Okay. Yeah, in the one-to-one mapping, of course we will have this kind of matrix. This matrix is very similar to if you consider from. Yeah, but for this one-to-one mapping, it's just all the elements inside the mapping is 1 or 0. Here we want to consider, can we do that? Can we do this thing? Can we do this thing? To many and without any training. Okay, without any training. How can we do that? It's like this previous work, one-on-one, one-to-one. And here is what we want, many-to-many. And we do not want any training precise to confirm the weights between YS and YT. Okay. Can we do that is the first question. It seems we cannot do that. So normally we will train the linear problem. We will just train this linear here, get its weight. But can we do it without training? The answer is yes. So now considering what we want to do in the supervised training, we always want to estimate this guy. Okay, YT given XT, that's what we want. Okay, that's it. And what do we have? What do we have at hand? What we have is a pre-trained model, right? What we have is a pre-trained model. So nature idea is that can we just link pre-trained model with this guy, Okay, that's our final aim. Can we link pre-trained model's output with our final aim? The answer is yes. This one is a pre-trained model. This xt is a ys given xt. Ys given xt. It means that we give xt to our pre-trained model. And we got pre-trained model. We have all the logics, and even with after softmax, we got this kind of probability. What's probability is little given yt xt. What's probability is xt belongs to this little. So this xt belongs to this little. We know this guy. Okay, we know this guy. Yeah. So we have this guy here, and we have another one. So how to estimate this one? First, we can say this one is actually matched with the input reprogramming. We just resize xt, we give xt to the virtual model, we got the ys given probability ys given xt. Okay, we can get this one. And how to estimate this one? That's using the integration theory. So this is yt given ys xt. It is equal to the joint probability yt ys given xt over marginal probability ys given xt. And how to compute this one? The answer is we just count numbers. Because we can go through all the data side, all the images and image label pairs from our target domain to our pre-trained model. After we give all the xt to pre-trained model, we got ys as well. We got ys as well. So we can look at this example. Here we only have 4 images. And we got ground truth downstream labels, cat and dog. It's ground truth, it's what we want. That's our target classes, cat and dog. And we also got some predict pre-trained labels, predict pre-trained label pairs, we have 3. After we gave these target images to our pre-trained model, we will know how the pre-trained model looks like this image. Okay, they will give one result for this target image. So we can know how many times these two are paired. Okay, these two are paired. We only have 4 images here. Okay. Here you can say these two guys are paired twice, and these two are paired once, and these two are paired once. Okay, just one. So what's the probability? What's probability here? What's probability here? Just for this number over 4. We've got a probability table. This frequency table, this probability table, and this is a joint probability. And this guy is just the marginal probability for this joint probability table, and we got this marginal probability. Okay. So we have this guy, and then we have this guy. So we have this one. We have this one. This one is actually the weight. It's actually the weight between. It's actually the weight between y and y. Y. Yeah. So we can estimate by count numbers. Here is how we count numbers. We calculate how many times this event happening together. Happens together. Y t y s. How many times these two happens together? And we can estimate. And then we can estimate this one by multiplying this one. Here we introduce another parameter lambda because we might have some direct issues when we calculate it. Sometimes it might be zero. With this small lambda here, it's small. Yeah, and then here is an overflow for our method. It's quite similar with this k. It's just this k. It's just this formula. It's just this formula. We also consider another estimation for this probability. We introduce like this kind of confidence for xi, ys given xit, ys given xit. Yeah, but it's more heuristic solution. So works better if it's more heuristic solution. Okay, now let's look at results. We still consider to test our method on the different architecture. We also test our method on the regional model as well, but here we mainly show this result. And compared to the previous method is ILM, iterative label mapping. We just need to use this formula. So we just need to use this formula to compute yt given xt, and the performance is clear. It's about 5% improvement, 5% improvement compared to previous method. Improvement is clear. And then we also found that this kind of label mapping somehow can show like how the source labels, source classes connected to our target classes, And we can always give weights because all the weights here are the probability. Right? Here is probability. All the weights here is number between 0 and 1. So somehow we can explain more things. Yeah. We can look at how the prediction model to link their classes with downstream labels. Here, I think this guy does not appear in the internet, and so they just find something. I think they still find the quite relevant one. Even they find some animals, but these animals have a similar feature. Okay, with this guy. Yeah, so for this is just the connected with this. And for this one, significant efficacy law, and all the source domain. And for the source model, you can find that the classes match the most is also source. So it shows that there are some interpretability for this automatic to find how the source classes contributed to your target class. It's quite interesting. Yeah, and here we show more detailed case during the training. You can see at the very beginning, it's this selected one, the selected top three source classes for our target class, and it will change and finally change to this. Yeah, so still. It's still not that like that's a visual from visual perspective. We might say some relationship between the source classes and this target class, but it's still not like fully improved like this time. And the good thing is like I said if we got some considering if we have some like not boundary, okay, like very generally our target domain. It's like dog. We can find the quite relevant thing from a source model. say, okay, in a source domain, this kind of class is kind of relevant to this switch. Yeah, another part is we found that yeah, it's still interoperability. So because our weight is controlled by just by the formula. It's not learnable. It's not learnable, and we can say it's indeed we'll select some class for our downstream labels. We will select some pre-trained labels for our downstream labels, and below this part and this part, it's just the it's a linear problem. It's a linear problem. You find the weight is more confusable and does not provide what is the real mapping between the source and target. But here we didn't do anything to make sure this is the matrix. This is the matrix. We didn't do anything to make sure this matrix is sparse. But in the end, the calculated one is sparse. It's sparse. The calculated one is sparse. And show the relationship between the downstream labels and the production labels in English. In the end, it's sparse. Didn't do anything strange to that. Okay, so next part we'll talk beyond this.
Sorry, just because we're tight on time and you are over, so maybe the next part should be very, very quick.
Yeah, it is. It's a last part. So beyond this BLM, BLM is a patient guided method. So considering what we have in the BLM, we have the prediction model, right? We have prediction model, and we have a fully supervised data set. Right? And what is K in BLM is just a formula, this formula. And the prediction model is here. Prediction model is here. And if we consider the fully supervised data set, we will have this guy and this guy. And this one, we can directly compute this guy with different prediction models directly without any training, YTX. And we also have observation for what we can do, we can just compute this discrepancy between these two guys. For example, prosecute loss diagonal. And it will directly show how the prediction model performs on the target side. Here we do not have any training, we directly compute YTX. And we can't compute this one. That's training free. And we found that this index, this BLM based log likelihood, is quite relevant with the final accuracy. With accuracy after factoring. And it means that if we have some prediction model, for example, we have data set here, and we got 10 prediction models. We can just compute how it performs well on our prediction model, on our data set, right? Using our BLM based log likelihood. And then we can see the value. If this value is quite small, we will not select this prediction model. We will not select this model, and we will directly select models with relatively higher, compatibility between the prediction model and the data set. It can perform as a prediction model selection before the factoring. And we can say the relationship is quite clear. This chain is quite clear. And this one is final accuracy. It's not the it's final accuracy. It's accuracy after chain. Accuracy after factoring. And we also observed it for the linear plot. Although we say two outliers here, but for most cases, most data side, we can see this chain. We can see this chain. Yeah. And here it's a linear from accuracy. So I'm still saying the clear trend between the BLM based log likelihood and the final linear from accuracy. Yeah, I think that's all for today. I can skip the conclusion.